Hey everybody, this is the lecture on section 5.2, the characteristic polynomial. So, given an n by n matrix A, we saw in section 5.1 that scalar k is an eigenvalue of A if and only if the dimension of the null space of A minus Ki is bigger than or equal to 1. Right? That is, if and only if, well, if the null space has dimension bigger than or equal to 1, that's if and only if A does not, or A minus Ki, does not have n pivots, which is true if and only if what? The determinant of A minus, well, if and only if A, the inverse exists, if and only if the determinant of A minus Ki equals 0. Okay, so the determinant of A minus Ki with K left, I hate to use the same word twice, the determinant A minus Ki with K left unknown, we'll say, is therefore a polynomial of degree n in variable k, whose roots are precisely the eigenvalues of A. Right? So K was an eigenvalue if and only if the null space of this matrix has dimension at least 1. And it doesn't have just the trivial solution in the null space. But that's true if and only if the determinant of that matrix is 0. Okay, but when you leave K as an unknown, okay, this determinant just turns out to be a polynomial in K. And that polynomial in K, its roots, right, where it's equal to 0, are exactly the eigenvalues. Okay, so this polynomial, so the degree n polynomial in variable k determinant A minus Ki is called the characteristic polynomial of A. So, for example, what was it? 0, 1, 0 So 0, 0 minus 4. 1, 0, 4. 0, 1, 1. So let A equal this. I'll find its characteristic polynomials. And its eigenvalues. Okay, by the way, okay, so of course we did this, we said before in section 5.1 that the eigenvalues of A are 2, minus 2, and 1. Thus, the characteristic polynomial should be x minus 2, x plus 2, x minus 1, which is equal to x to the third minus 4x squared plus x minus x squared minus 4x plus 4. So that should, well, it should be k, sorry. K, so k squared, 4k. So that should be the characteristic polynomial, but let's verify that. Okay. So A is 0, 0 minus 4, 1, 0, 4, 0, 1, 1, minus k times I. So that's k times 1, 0, 0, 0, 1, 0, 0, 0, 1 is equal to, alright, so it's minus k, 0, 4, 1 minus k, 4, 0, 1, 1 minus k. Okay, so that's equal to a minus ki, where we don't specify what k is, we make it as an unknown. So now the determinant of this matrix, now unfortunately you can't really do this determinant other than by doing a cofactor expansion. You can't really do, well, I mean you could do row reductions, but it's really sort of tricky with the variable k. Yeah. Okay. Double check this. So yeah, that's minus 4 there. Minus 4. Okay, so now we want to take the determinant of this. So rewrite the first two columns, like that, and we'll do the products. So this is k squared times 1 minus k. Right, k squared times 1 minus k, 0, minus 4, right, and then the backwards diagonals, minus 4k, plus 4k, right, wait, something wrong. This is 0. This is minus 4k, so that becomes plus 4k, and then this is 0. So we've got k squared minus k to the third minus 4 plus 4k. So rewriting that, this is minus k to the third plus k squared minus 4k, plus 4k minus 4, which is the negative of that. Minus k, so it's plus, minus, minus, plus. No, something went wrong. What did we do? Oh, no, that's right. Plus, minus, minus, plus. And this one is minus, plus, plus, minus. So this is just the negative of what we had before, what we thought it should be. K to the third minus k squared minus 4k plus 4. But, I mean, negating a polynomial doesn't change its roots, correct? I mean, you can put any scalar out front here, and then the roots are still the same, because you always divide it out in an equation set equal to 0. So this is the expected. Characteristic polynomial. Alright, so this should be plus or minus this, which is plus or minus that. Alright. Let's try a different one. So find all eigenvalues for a equal to 0, 1, 0, 0, 0, 1, minus 2, 3, 0. Okay? Well, a minus ki is equal to, so you just put minus k's along the diagonal. Minus k, 0, minus 2, 0, minus k, 1 minus 3k, 0, 1 minus k. Okay, so the determinant, minus k, 0, minus 2, 1 minus k, 3, 0, 1 minus k, right over the first two columns. 0 minus k, 1 equals, so we have minus k to the third, 0 minus 2, minus 0 plus 3k, so minus minus 3k is plus 3k, and then 0. So this is the negative of k to the third minus 3k plus 2. Okay, so we find the eigenvalues by solving k to the third minus 3k plus 2 equal to 0. Now, how do you solve a degree 3 polynomial equation? You can't use the quadratic equation, but what we usually do here in this case is to first look for a rational root. Okay, so a rational root of a polynomial with leading coefficient 1 is always a divisor of the constant term. So the possible rational roots of the polynomial are plus or minus 1, plus or minus 2. So let's try those. Okay, so let's try 1. 1 minus 3 plus 2, well, that's 0. So k equal to 1 is a root. So now that we have that root, what we can do is divide it out of here. So k minus 1 is a root, so k minus 1 divides into k to the third minus 3k plus 2. So k minus 1 divided into k to the third minus plus 0 minus 3k plus 2. So we'll put a 0 in where that k squared should be. So we multiply this by k squared, and we get k to the third minus k squared, and you want to subtract that. So this is k squared minus 3k plus 2. Multiply this by k. So this is going to be k squared minus k, and we're going to subtract that. So this is minus 2k plus 2. So then minus 2, 0. Alright, so what was the polynomial? K to the third minus k plus 2 is equal to k minus 1 times this, k squared plus k minus 2, the quotient. Right? You divided k minus 1 into here, and it gives you an even quotient because you have remainder 0. Alright, now this one, hopefully you can factor it, or you can find the roots using the quadratic equation. But anyway, this one is k plus 2, k minus 1. Alright, so eigenvalues of A are 1, minus 1, and minus 2. So notice that because the degree of the characteristic polynomial of an n by n matrix A is also n. Okay, there are at most n eigenvalues, distinct eigenvalues, for A. Okay, so you don't have to have exactly n, you could have less than that, because, polynomials have repeated roots sometimes. Right? A degree 3 polynomial could have a repeated root. This one has, oh no, I'm sorry, oops. This is k minus 1 squared times k plus 2. This one does have a repeated root. So the eigenvalues of A are 1 and minus 2. So we only have 2 distinct eigenvalues because that characteristic polynomial has a repeated root. So you can have, for a 3 by 3 matrix, up to 3 eigenvalues, but you don't have to. Okay, you're always going to have at least 1, but you could have 2. Okay, 1, 2, or 3. All right. Okay. Next, similarity. So this is a different topic that we're going to use in section 5.3. Where we're going to do something pretty cool in section 5.3. Anyway, similar matrices. An n by n matrix A we say that A is similar to B when there exists an invertible matrix P such that B is equal to PAP inverse. Okay, an n by n matrix A is similar to B when there exists this P such that B is PAP inverse. By the way, if A is similar to B, then B is equal to PAP inverse. So therefore, BP is PA, right? Multiplying both sides by P. BP is PA, P inverse P. So BP is PA. Some more space. Now multiplying by P inverse on the left. So P inverse BP is equal to P inverse PA. So P inverse BP is equal to A. Therefore, right, A is similar to B if and only if B is similar to A. If and only if B is similar to A. So it's a symmetric relationship, right? Which not all relationships are, right? Less than is not a symmetric relationship. 3 is less than 4, but 4 is not less than 3. So that's an anti-symmetric relationship. It's never symmetric, but this one is a symmetric relationship. Okay. And then the special property of similar matrices that we're going to be concerned with is the following. If A is similar to B, then A and B have the same eigenvalues because they have the same characteristic polynomial. Okay, so proof of that is as follows. Okay, so the characteristic polynomial of B equal to PA inverse is, right, the determinant of B minus KI, right, but this is equal to, let's see, is this. So now, not that. Is equal to, well, it's the determinant. B is equal to PAP inverse. It's similar to A minus KI. But I is equal to PIP inverse, right? Because I times any matrix is the same matrix back. Right? I is PIP inverse, right? PIP inverse is equal to, well, P times I is P, is equal to I. So why don't we write that down? So now, because PIP inverse is equal to PP inverse is equal to I, we get that. So let's do that all in one step there. Whoa. K P I P inverse is equal to, so we factor out P on the left, P inverse on the right. Determinant P A minus K I P inverse. Right? P is on the left of each term, and P inverse is on the right of each term. So we can factor out, and K is just a scalar, so we can put the K wherever we like. Which is equal to, well, the determinant of a product is the product of the determinants. Determinant P inverse. All right, but the determinant of P inverse is 1 over the determinant of P. All right, so those guys cancel. Because multiplication is commutative, you can do that. A minus Ki, which is the characteristic polynomial, of A, right? This is the characteristic polynomial of A, and it's equal to the characteristic polynomial of B. Okay? Done. So, for example, and this leads right into section 5.3, let D be this diagonal matrix 2, 2, minus 3. Right? With the diagonal matrix, the characteristic polynomial of D is, well, it's the determinant of 2 minus K, 0, 2 minus K, 0, 0, minus 3 minus K. Right, so this determinant is equal to 2 minus K, 2 minus K, 3 minus K, 3 plus K. Right, so the eigenvalues are 2 and minus 3. Okay. So the eigenvalues of the diagonal matrix are 2 and minus 3. In fact, the eigenvalues of any diagonal matrix are simply the entries along the diagonal. Okay, so now consider, let P equal 1, 0, 0, 1, 1, 0, 1, 2, 1, and so P inverse is equal to, so here's just a matrix I know. Okay, they're almost the same, but not exactly. So let P and P inverse be equal to this. So 1, 0, 0, 1, 1, 0, 1, 2, 1 times that diagonal matrix 2, 2, negative 3, 2, 0, 0, 0, 2, 0, 0, 0, minus 3, 1, 0, 0, minus 1, 1, 0, 1, negative 2, 1, like that, is equal to, well, let's multiply these first. Oops, that's a 2. When you multiply the diagonal matrix, the first column is on the left. The first column is going to be 2 times the first column here. So that's 2, 2, 2, right? It's 2 plus 0 plus 0, 2 plus 0 plus 0. So first row, first column is 2 plus 0 plus 0. Second column is 2 plus 2. Or first row, first column 2, 0, 0. First row, second column is 0, 0, 0, 0, 0, 0. So this is 2, 0, 0, 2, 2, 0, and then minus 3, minus 6, minus 3 times this guy here. 1, minus 1, 1, 0, 1, 1, 0, 0, 1. Double check that. So now, second row, 2, 0, 0, 0, 2, 0, 0, 0, 0. Third is 2, 0, 0, 0, 4, 0. Oh, wait a minute. Third row, first column. 2 plus 0 plus 0. 0 plus 4 plus 0. 0 plus 0 minus 3. Okay, so that's correct now. We multiply the diagonal matrix on the right, and therefore it scales the columns. So 2, 2, 2, 0, 2, 4, 0, 0, minus 3. And then multiplying this, first row, first column, 2 plus 0 plus 0, 0, 0, 0, 0, 0, 0, and then 2 minus 2 plus 0, 0, 2, 0, 0, 0, 0. I'll make the diagonal again. 1 minus 4. So 2 minus 4 minus 2 minus 3. 2 minus 4 minus 3. So that's minus 5. Okay, it's not. 0, 4 plus 6 is 10. And 0, 0 minus 3. Alright, so this is the product that you get. So the eigenvalues, well, the characteristic polynomial and eigenvalues of 2, 0, 0, 0, 2, 0, minus 5, 10, minus 3 are the same. Is 2 minus k, 2 minus k, 3 plus k. And 2 and minus 3. So the characteristic polynomial and eigenvalues of this matrix are the same as that for A, which are the same as that for A. So this is PAP inverse, which is this, they're the same as that for A. And the reason why is not hard to see in this case, I mean, other than the theorem we just proved, is that this is a triangular matrix. And because it's a triangular matrix, the determinant is just what's along the diagonal. So even though it's not a diagonal matrix, it's a triangular matrix. Okay, that is the lecture for this section.